啊，在电上体验
嗯，其实特别多，
好，
对，特别多，也有明显对，哦，对吧？然后
嗯，OK，回答我觉得我他们是在都可以企业在也是有很强的这个一定，然后那个 Flash 我比较可以把它这个而且 OK 往有还这件事，这个分摊这个所以还是我觉得一个哎，那这个是人对吧？就发展到就是了解包括方的关系跟一个一些我们要聊technical cybernetics 就是这个可以说的有点难，描述一些当时的来就是在人对吧？都在对这 structure 这个我只是然后到时我一个是哎，相当于设计，但是这对还是这个也是相当于国民的，但是越大的意义，会往这个来，就是关于实验的，然后越来为什么都是按关但是我觉得要是它肯定会都行，拿不到了，那个案子，对，当然也opportunity to have that 干嘛好 fire 你要不弄 that is develop more now outbreak or to what he has so the plan is to work on the thank you also the pleasure for me to be here your time really nice really glad warm welcome here thank you very comfortable here come on okay everybody get this here okay if you hear look at also and thank you before this talk is about Lidar-Assisted Control in the background our Wind turbine and Flensburg University currently has three Lidar-Assisted laws. The main idea is to make the wind turbine cheap. Because normal wind turbine. So this is also our main motivation for the Lidar-Assisted Control because wind is a very complex disturbance and it's changing not over space but also time. And as I mentioned before, normal wind turbines are blind, so they cannot see the wind. So they can only react to changes in the wind after the storm already had an impact on the structure of the turbine. So generally the rotor will accelerate or power the blade will back before the wind turbine reacts. Now, with the LiDAR technology, we can measure in front of the turbine and somehow predict the future. And we know that from daily applications that knowing your disturbance in advance makes a lot of sense and improve control performance. And you have that in daily applications. For example, if you're riding your bicycle and you open your eyes, way more comfortable. Because if you close your eyes, you really have to bump into your obstacles besides the way around. In a similar way, we predict that if the wind turbine can see the wind, it can operate more smoothly and therefore be more cost effective. So the two main questions we have in this research and also lecture today is how can we get useful wind video signals from the raw LiDAR data, and also then the second question is how can we then use these signals to improve wind turbine control. And we will first look into the Taylor wind turbine model, and then also in the wind field reconstruction and the correlation model to see how good are LiDAR or the wind preview quality. Finally, we will see the most promising control approach with the selective power control. I will present some current results we have in our research project, and at the end, it's future for other ideas that conclude. About this Taylor wind turbine and LiDAR models. So this is important. Why? Because we in control engineering do a lot of model-based approach. So it's good to know a little bit more about our wind, the wind turbine, and also the LiDAR itself. So the wind usually is considered to be time-varying 3D vector field. What does this mean? It means that wind here is three-dimensional vector defined on a grid. And the turbulence is defined along the mean wind direction. And the mean wind direction can be inclined with horizontal or vertical with your rotation. However, this understanding of wind is used a lot for simulation, but it's too complex for control of the time. Therefore, we have this reduced wind understanding. So here we have a rotor-active wind and linear horizontal and vertical here. And we further assume that the structure will travel unchanged towards the rotor with the mean wind speed. And this is called the Taylor-Frozen turbulence hypothesis. And this is very useful for the timing. Not when for LiDAR system controls, we need to know exactly when any change will arrive. Okay, then about LiDAR systems, I think Stu can explain much better how LiDAR works. So I will refer to his lectures about LiDAR in general. So far, we just need a mathematical model of it. So we have a very simplified understanding for LiDAR system control. So we can either use a point model where we have our wind vector u in W, the three-dimensional vector, right? And we can with LiDAR only measure the wind component in line of sight direction. So this here is our LiDAR vector. Then we will measure only the product of those vectors, which we call line of sight. As I mentioned, usually this is positive if the wind is towards the light system. And in mathematical sense, that's the projection of the normalized vector of the Fermi. If the light is moving, then of course this value is superposed with the motion of the lidar itself. So here the lidar should move also in x, y, z directions, and then the line of sight will be slightly different. This is, for example, important for floating lidar or for lidar on a floating wind turbine. And should I go back again? That we can continue. Okay. Yeah. So this is a point measurement model for LiDAR, which we use a lot for estimate. We have okay. Further, we have a volume measurement model we use for simulation. It's a bit more detailed. So here we consider measurement volume. Since we are not measuring in a small point, we are measuring along the LiDAR beam, right? So if we are our LiDAR beam goes this way, then we are measure always along the beam as well. And how can we express that in a model? So we integrate along here the distance before and after the focus point. And for us, a LiDAR system, we have a constant volume over the distance. And there's another technology called continuous wave LiDAR. Here, typically, the weighting function looks different and is also increasing with the distance squared. So if you measure twice the distance, this is 4 times the measurement block. Okay, how about wind turbine model? So there are a lot of different types of wind turbine models, but the most common are aeroelastic tools. And one famous representation of this type of models is the SPARC software. SPARC is the Speed Aerodynamic Structure Equivalent. It's developed by the National Renewable Energy Lab in the US. And it's open source. Now it's also called Open SPARC. And typically we have the 16 degrees freedom to use 3D turbulent wind speed. And the aerodynamics are typically calculated by plate element momentum theory in iterative calculation. So this type of models are considered to be sufficiently realistic for a low simulation. It can also be with certification. However, it's too complex for our control purpose. So here we have a more simplified model. We call it a simplified wind turbine, where we only consider the states we need. And in this case, for lidar control, it's enough for now to consider the rotor motion here and power top motion, and we only consider 2 control inputs with a selective shift and the generator torque, and further only one scalar disturbance, the root effect between. And just with these other models, we think is sufficiently accurate for control of design and also for lidar control. So about the reduced order model, the rotor motion we typically model with the law of conservation of angular momentum, the case with inertia, and then we have the rotor acceleration here, and this is equal to the sum of all moments acting in the rotor, aerodynamic moment, and the generator torque multiplied with the gearbox. Then the power motion typically is modeled by simply mass spring damper system. Here we have the aerodynamic thrust. The aerodynamics are a bit more complicated. Here we have the aerodynamic torque, which depends on the power in the wind, which is 1/2 times the air density, the rotor area, and the wind speed per cube. And then we multiply with the P to get the power of the wind. The P is the power coefficient, depending on the pitch angle and the pitch speed ratio. And then we divide by the rotor. The thrust looks quite similar. So again, we have on 1/2 air density, rotor area, here the wind speed squared, and we multiply it with P, which is the thrust coefficient. Again, it depends on the pitch angle, but also on the pitch speed ratio. And for the pitch speed ratio, here we use the relative wind speed, since the turbine is moving back and forth. This is our top speed, which we got, and this we use also here for the wind speed equation and to get the aerodynamic damping. Okay, now we have all the models we need from the LiDAR, from the wind, and from our wind turbines. And now we can see how we can use those models to build up our LiDAR system further. And the first thing is the wind field reconstruction. So in the wind field reconstruction, we consider the LiDAR to be a system with no input. In this case, it's the scan parameter. Then we have measurable output. In a specific case, it's the line of sight wind speed. And then we have a disturbance. And the disturbance here is the original wind field. And the idea of the wind field reconstruction is that use those inputs and outputs to reconstruct as good as possible our wind field. And there are a lot of approaches, for systems engineering, a lot of times they usually are called observers. And the main issue we face here is something which is called the cyclops dilemma. So as a cyclops, only one eye cannot really be three-dimensional. The same is happening on LiDAR, because we only measure line of sight. So here again, we have our wind vector, our laser vector, and we measure the line of sight. However, any of the wind vectors here will cause exactly the same line of sight. So we cannot be sure when we only measure line of sight which of these wind vectors has been present when we did our measurement. So, but the good news is we can still provide good estimates of our wind with adequate wind models. And those wind models depend on the application. So you need different models for estimating your wind. So the easiest application is for cloud-based systems. And here you can first think a bit how would you simulate LiDAR. And just like a very basic cloud-based LiDAR system where we have a measurement in 4 E's. Typically, we measure in the north, south, east, and west. So we get 4 lines of sight. Now, when we assume that the wind in all 4 E's is the same, maybe over 10-year averages, it's also quite low. Also, when we have a flat terrain, then that's a good assumption. Then we can simulate our line of sight with the same equation we had before. So when we express this equation here for 4 measurements, we can put it into this metric format because we assume that the UVW is the same vector here for all 4 points. Then this sinus here with cosine, depending on the opening angle alpha L here, there's nothing else as the x, y, c in this equation. That's the normalized vector. Okay, then we can call this M, we can call this A, and this S. Yes, very good. How can we use this equation to get our first variables? Then we have our measurement. So this is, let's say, how we simulate our measurement when we know UW, but in a real application, we will measure M, and we want to know our UVW. So what can we do? Any idea? We have a matrix A, a vector S, and a vector M. Now we know M, we know A, we want S. What will we do? Yeah, exactly. So you can divide by A or like make it inverse. So in this case, A is 4 by 3, so we cannot get an exact inverse, but we can use something which is called the pseudo inverse. Often we express it A plus, and this A plus also is the solution to the least square problem, like fitting AS to our measurement. And this A plus matrix looks like that. So which means we get a VU component by combining the north and the south component. We get the V component from the west and the east component, and the W component we get from all 4. And this equation here is also equal to the official equation typically those 4 being the ground-based systems are using. So what do we learn from this? We learn that the reconstruction process is something inverse in simulation. And we also learn that if there is no error, then both models are identical. Or we have no error if those models are identical. So we can perfectly reconstruct. So we wanted to test this assumption, and during my PhD, some time ago already. So we had one of the first LiDAR systems for wind energy. So this is a wind tube from a company which at this time was called Schlipf, now it's called Lidar-Assisted. And this was the wind tube number 4. So was one of the very early systems. And we got a second casing for Stuttgart wind energy tube, and we installed it also at NREL on a turbine. And the main challenge the first 2 years of my PhD was to coordinate the software of the laser with the software, like the motion controller of this mirror. So we had a hidden mirror we could move, and this we were quite flexible. We could redirect the beam to any direction within a certain window. And before we went to NREL, actually we had it installed at ETU. I think you have been working maybe over here was your office, right? This direction. You may know this path secure. And there's a small little map. And we put the LiDAR here on the ground to line such that we could measure to the left and to the right of the sonic anemometer. Sonic is here where the Schlipf is here. And then we were assuming there is no W component. Denmark is very flat, and therefore we only had the simple equation here. So 2 lines of sight, we have our x and y coordinates of those points, and then it's easy to get u and v by simply having the inverse matrix. And those are the results. So 10 minutes analysis of the LiDAR U W component, LiDAR is 0, and you can see that W component was okay almost 0. good agreement. So this proved a bit that our assumptions were okay. And then we thought, okay, how can we also prove that works in complex terrain? Because in complex terrain, you cannot make this assumption up to zero. And therefore, we were reconstructing the wind in the Lidar coordinate system, which is the one inclined, and we ignored the information about the terrain. And then we had a more complex trajectory, 3x3 trajectory, and then we tried how we can best reconstruct the UVW point again. And in this case, we use those 12 points in the red circle to get also a very good agreement in the UVW component within this Lidar coordinate system. And here we use this least square minimization and a nonlinear model, which I presented at the beginning, the vertical sphere and the insert. Okay, so this is for ground-based system. So as I mentioned before, in the wind construction, you need models according to your application. So we have seen for the flat terrain, a simple model is enough. For complex terrain, you need already for complex model. How is it for floating lidar? So a floating lidar is a basically the same like mounted. So here we have another example of ground-based lidar. For example, continuous wave lidar, they are measuring on more than 4 points. If they're measuring on circles, typically it's like 50 points. So in this case, you can apply the VID approach, which is basically the same as I mentioned before. You can calculate your A matrix and then get your UVW by the inverse. So they also do like a fitting process, but at the end, mathematically. Okay, but what's now happening if we have waves? Then the Lidar and the inertial coordinate system will do not the same. You will work with Lidar, right? With floating Lidar. And then you will have the problem that the Lidar is measuring not exactly in the surface. It will be depending on your motions in a very complex figure, like here, this red. And how can you then reconstruct the wind? And here, if you understood how the simulation would work, then you can also use the same model for reconstruction. So, in this case, we just need to find always the A metric which was present during the measurement. So we need to get our A metric from measurement. So we need to measure how the lidar will move. And there are like instruments like IMUs, like the measurement unit, which can provide you not only the angle, but also the position of your line. And then you can simply update your A matrix with the real measurement position. And then you can again just make the inverse of A, but this inverse of A will be always changed. On ground-based lidar, it will not change, but for floating lidar, it will change. And there might be additional correction for the velocity useful, and also might be useful to use a non-linear model with the vertical ratio. And what's very important for that are coordinate transformations. I also I said it during the lecture this week. In general, your mathematical background will be very important in the future if you do research or also even work for industry. So you can save a lot of time if you invest time now learning well your subject. And for example, for coordinate transformation, you would say, oh, that's something very simple. I had the bachelor, it's totally clear. But it's not so super obvious. At least I have a lot of different industrial processes where exactly this coordinate transformation took a lot of time. Why? Because there are a lot of different understandings of coordinate transformation. And for example, here, for simple rotation, there are already 6 different possibilities how to do it, and those are called Euler angles. The most common, at least I know, is from the aircraft design norm, where you first do the yaw, then the pitch, and then the roll. So the first, the yaw is always the rotation around the z-axis, then the roll is around the already rotated y-axis, therefore we call it a prime, and then the roll, the pitch is about the y-axis, and then the roll will be around the x-axis, which has been stated already twice, therefore it's like a double prime. There are 5 other possibilities for this coordinate transformation, and you need to know what coordinate system is your measurement system assuming. Then you can use it also for correcting your lighting. So in this case, you then multiply the yaw with row instead of the rotation order, and then you can transform any Lidar coordinate into the inertia coordinate. Okay. If you have done a Lidar, floating Lidar, how can you correct the velocity as well, right? Because the Lidar is not only measuring as well, it's also constantly in motion. And once again, here it helps to have our simplified measurement equation, because here we see the impact of our motion. So when we know that, we can simply invert the effect. So when we have our measured line of sight, and here x multiplied is the x speed, our y multiplied is the y speed, and c multiplied is the speed, and everything needs to be in the inertia coordinate system, then we will cancel out this effect of the Lidar motion, and finally get the motion compensated line of sight. And then we can continue with this motion compensated line of sight for whatever we want to do, like for the wind turbine. And in general, for the wind turbine construction, for this model-based approach, we have this general idea, right? So with this dimension angle and the line of sight velocity, we can then, together with the wind model and the Lidar model, and initial values fit our simulated measurement onto the measured Lidar measurement. So this fitting process, which you can do with the square approach, finally gives you then your fitted wind field characteristics. This could be, as I mentioned before, clear wind direction, wind speed, and so on. And then you know more or less the whole wind field in your assumed domain, and then you can reconstruct the wind with your location of interest. So, for example, we could also use models for wave or for the induction zone to reconstruct the gradient. And this is what we tried together with VQ. It is some years already ago, where we had a Lidar installed for wind turbines, 2 Lidars basically. One was a continuous wave, and one was a Lidar system, in this case with 5 beams. And we had a net mass located at 2.5 meters distance. But for power performance applications, we need to have measurements outside of the induction. And 2.5 is more or less considered to be outside of the induction zone, even that it's not really true. But we can then use only measurements even close to the rotor, and then use like the wind field construction to extrapolate on this point. And for the induction zone, we model the induction zone with this equation. So the free wind speed here multiplied with this equation depending on the rotor radius, the distance, gives us then together with induction factor, gives us then the wind speed at every position in front of the turbine. So because the wind speed will go down when we go forward the turbine because we have energy. And this can be modeled with this equation. Just like one induction model, we can also have a PDU. And then we compare it to our measurement. So when we have our measurements in 2D or 2.5D, we could, without this induction current model, we got very good agreement. So this is the R2, and again, comparing here our up measurement with either the 5D or the continuous wave line system. So both had very good. But when we use only measurements very close to the rotor, we would get wrong results. But when we use our induction current model, we can get again back to the same quality level as with the measurement at 2 and 2.5. Why is this a good idea to measure close? For flat terrain, it's no problem, you can measure 2.5. Right? But in complex terrain, it's sometimes better to measure close because far away there might be some obstacle or the flow will totally different. And another application might be for very large rotors. Because for very large rotors, we need to measure very far away, and then the wind traveling towards the rotor might be uncorrelated already. Okay, that's another idea why wind field construction is important. Finally, going back to control. So in the previous application, we were focusing more on 10-minute averages for power performance or wind assessment purpose. But for control, we need high resolution data, and we also need to adjust those ideas to either muscle or spinner based. And the other thing, we need to synchronize it with control. Right? So it doesn't help if we say, okay, there was 5 seconds ago. The control system needs to know, okay, there will be a one. And we are also not interested in single point measurement. Before, we always compared it to measurement, right? But we are not so interested in single point like a measurement. We are interested on the effect on the whole rotor. And the simplest way we could do here what we call dynamic construction is using frozen turbulence hypothesis. So, for example, this is a side view of our antenna we had at Stuttgart University. So here we were able to measure in 5 distances and a lot of points. Nowadays, commercial lighting system, like also the one here of the university, is measuring in 10 distances or even more, right? And typically we are 40. And then we can combine every distance to one signal, and then with frozen turbulence hypothesis, calculate the time it needs to travel, for example, to the first distance, and then we can combine everything. And we also assume that perfect alignment. So we assume W and V are 0, and then we can combine it easily to one signal. In the next step, we can then filter the signal. I will explain later why filtering is important. And as we learned on the lecture yesterday, all filters have a time delay, right? So it will be delayed. And then maybe we need to buffer it a little bit before sending it to the forward input. So typically we need the signal a little bit before the wind hits the rotor. Why? Because we need some time to react with the wave. Okay. So there are some more advanced LiDAR data processing algorithms than the one I presented. Because the one I presented we use since more than 10 years. So the issue of this conventional LiDAR data processing is that typically the amount of previews unknown, and also the preview time changes with the new input. And also typically the signal includes uncorrelated wind if you don't use surface. And we have developed in our company concept which is called the moving horizon lidar data processing, and it always gives you over big horizon. So in every point of time, you get the event from signal to, for example, 12 seconds. And you know, the thing is this guy will be a vector every time. And it will be also like here, also in the way that our uncorrelated to move. That's very helpful for control. For example, something which is called model predictive. And the has been tested already been over a year now in Mongolia. And we really hope we can publish soon those results. It was together with another German company which is specialized in automation. So they did nonlinear model predictive control, and it was running on a 6 megawatt turbine. The rotor diameter was over 200 meters. From what I've heard, and the field testing was very successful. Then there are other ideas, mostly using area slope equation. For example, there's a paper where they use a filter and area slope equation to estimate the wind field, or like here in this figure, you can also use the networks together with LAS simulations to reconstruct the flow field. There's another idea from a PhD student from PTU was visiting in Flensburg for some months, where he's using proper orthogonal decomposition. It's also quite well known for flow field reconstruction. And he was like using more complex end pattern of spinner-based lidar, and we were able also to reconstruct the wind field in very high resolution. So this is more like the future of wind field reconstruction. So there's a lot of things still going on, and very interesting as well. We can use a lot of modern algorithms. So how can you evaluate your reconstructed wind? Before we were always comparing it to MATLAB, only ethics. But when you want to compare it to high resolution and affect the rotor itself is the best measurement. And here again, this model we also use a lot in the lecture, right? So we have here our inertia, rotor acceleration, aerodynamic moment, rate of torque, gearbox ratio, and in this equation, everything can be measured except the rotor effective wind speed. Right, we can measure the air density, rotor speed, pitch angle, and the rate of torque, but the wind speed not. So we can use this equation then to get or estimate the rotor effective wind speed. It's not so super straightforward. Why? Because of this CP, where we have some speed ratio also included our wind speed, but you can there are several approaches for that. And then you can compare that with your lidar measurement. So this here were like the first 5 minutes we collected when we sent our lidar to NREL, and finally got it working. And it was so nice for us during the really first time of lidar-assisted control to see this agreement. So here we can see turbine for turbine and do the lidar, how lidar works with the thermal pattern before it's turbine. And here we are using predefined dynamic wind speed. And what you can see here also that the last trend is very similar. But there are small details where the two differ. And this we were investigating then with the correlation method, which we will see now in the next chapter. So this chapter is about how can we calculate the wind speed equality. How can we improve it as well? And how can we first measure wind speed equality? You can have different measurement criteria. What we use a lot for control is something which is called coherence. So you can always calculate the coherence between two signals. In this case, is the light estimate of the root effective wind speed and the real root effective wind. And you can display it over frequency or wave number. So the wave number is the same in space what angular frequency is defined. And there's a clear connection between frequency and wave number here in wind speed. But for some reason I will explain later, it's better to display over wave number. So also wave number can be considered to be inverse proportional to the eddy size of your turbine. So this is the example of a coherence between the rotor and the Lidar from simulation. How can we get it? So we can first use the turbulence model. In this case, for simple IEC turbulence model. We use inverse FFT to generate our wind field. So we will see that in the lecture next Monday how to do it. And then we can use a Lidar simulator to scan this wind field. We can then also use our wind field construction algorithm and simulation, and then we get those signals, and then we can do an FFT, and then we get this coherence here. So like with the FFT, we can calculate auto and first spectrum, and then we estimate the coherence. It's pretty time consuming, right? And at the end, you get something like this. It's a pretty noisy, just based on 1 hour of simulation. And when you want to determine the quality as a scalar value, for example, the bandwidth at 0.5, it's not really clear where it will drop. Like 0.5 line here, right? And will drop several times. What's much better is to model this coherence directly in the frequency, right? Instead of going from frequency to time and back to frequency, it just stays in the frequency, which means we need to find Fourier transform of our Lidar simulator, and that with this we can then calculate directly the coherence. And this can be done in a fast and automated. Once again, this correlation model helps us to understand wind speed equality, and we can directly calculate how well the Lidar will measure. So we don't need to do expensive field tests with the turbine and Lidar. We just calculate it. How this is done? So this is the definition of coherence, right? The coherence in general is defined as the cross spectrum squared and absolute value divided by the outer spectrum of the two signals. How can we model that? So here we can, for example, the outer spectrum of the rotor model based on the time equation and Fourier transform. So this here is the time domain equation. So our root effective wind speed we define to be the mean of all these components hitting the rotor. Then we can do a Fourier transform of this and multiply it with the conjugate complex Fourier transform. And if you hopefully still know, is that the Fourier transform is a linear operator, which means instead of making the Fourier transform of the whole thing, you can just do it for every component. And then you can combine always the Fourier transform of one component with the Fourier transform of another U component. And this is nothing else as the cross spectrum in those two points. At the end, you can also express the cross spectrum by multiplication of the coherence and the outer spectrum of which is every point has the same outer spectrum, and you end up with this equation here. So the graph are all the coherences of all combinations at once. And this coherence is defined in turbulence models, the Hellman model, or the more complex reactor model, and then you get your outer spectrum in an analytic form of the rotor. You can do the same with the Lidar. It's a bit more complex because you have to find Fourier transforms for the temporal spatial averaging, for the discrete Henning, the wind construction algorithm, and also you can include wind evolution because the wind will change from the measurement towards the rotor. And the cross spectrum at the end is just a combination of the two results. Looks pretty complex, but at the end it's not so complex in the automated system. But for now, it's important that we remember the coherent Henry model by auto and cross spectra, and it's based on Fourier transform of the measurement equation. So once again, basic mathematics, basic mechanics, get this well done, and then we will save a lot of time to speak. Okay. You can also use this idea to design a filter. So why do we need a filter? So here you can see a typical line-axis control loop. So first we have our wind field in front of the rotor. It will change traveling towards the turbine, and then the rotor-affected wind speed will affect our wind turbine. We have measured output. We feed into the controller, and with the control input, we will then operate the turbine. Now, with the lidar system, which is measuring the wind field in front of the rotor, we get our lidar data. With the wind field constructed, we will get our lidar estimate of the rotor-affected wind speed. And to use it in our controller, we need to find something which is as close as possible to the real rotor-affected wind speed, such that we can use it. Another way how to see it is that we need to filter out all uncorrelated frequencies to avoid unnecessary and also harmful control actions. Because all the high resolution data we have with our wind field estimate will only cause, for example, when we use it for pitch control, to pitch without any effect, because the small turbulence eddies, they'll already change totally or even went different ways, so we don't need to compensate. And even when we do it, it will have negative. So how can we now use the correlation model to define a filter? So we can calculate the transfer function from our rotor estimate to the real rotor-affected wind speed, either from data or from our model. So we do this the transfer function from the previous block, from the method campaign number, and the transfer function nothing else spectrum divided by out lidar, or you can also model it. Then you can give a linear tool to best represent those lines. Or you can use something which is called Wheeler filter. It is basically the red line directly to remove all the uncorrelated features. Another application of this correlation model is the scan optimization. So during my PhD, I optimized this scanning lidar of SWE for this 105 megawatt turbine to get the best coherence bandwidth by changing the number of points. So we could measure in more points than in we could adjust the number of points on the circuit, and we could also change the first measurement distance. So the last measurement distance was fixed due to the setup, but this was flexible, the first distance in a certain range, and also the normalized radius, like the opening angle, we could cut up. And in this optimization, so we did like a brute force optimization with different number of points and different normalized radar radius and different first distances. And here the best was 8 points. So you might think the more measurement points, the better the preview quality is. But in this case, not. So in this case, 8 was better than 12. What could be the reason? Any idea? Why is measuring in more points not always helpful? So in this case, if you're measuring, for example, on the right side, with a lot of points, which takes time, you could miss something on the left side, right? Or the other way around. So the problem is, more points take more time to do a circle. And for this reason, the quality will go down. Right? So you need to good distribute the measurement points in time and space. Okay. For people, this measurement coherent bandwidth was often a bit hard to understand. Therefore, we try to normalize that. So here we came up with the idea of the small detectable eddy size, but with a turbulence factor which is still detectable with a reasonable quality by a LiDAR. So it's the inverse of the coherence bandwidth and normalized by the rotor line. And if you have 1D, it's a very good LiDAR, and you don't need to be better than 1D if you only have collective pitch. 1.5D is a good LiDAR. 2D would be kind of average LiDAR. And then 3D is kind of still sufficient for LiDAR physical control. We even use a LiDAR once with 5D measurement qualities, but yeah, then at a certain point, the information is not so helpful. Okay, so now we know how to reconstruct the wind, to generate signals, we know how to filter the signal, and in the next part, we will learn now how to use it for control. And the most promising concept is here the collective big thought. Do you need a break, or can you continue? Okay, it's okay. Yeah. Then let's stop here before we go to the control concept. 5 minutes. So back at 306. Yeah. then let's continue. Okay, so next part is now about collective pitch report control. As I said, it's the most promising of the Lidar-Assisted control concept. First of all, I would like to introduce to those who are not familiar with Lidar-Assisted wind turbine control and the wind turbine control. So we have in general three main control regions for wind turbine control. In the region 1, the wind speed is too low, so we have no power generation. Then in region 2, which is typically from maybe 4, 5 up to 10 meters per second, we have the region 2, where the control is to maximize the energy needed. Then in region 3, we have maximum power already reached, because we have to design the wind turbine for certain power levels. And the control goal here is to maintain rated power and also rated generator speed and reduce the structural load, because the wind is for free, but the wind turbine not. So we have to reduce the load to operate the wind turbine if possible until the end of the defined life. And of course, there's some transition regions 1.5 and 3.5. Baseline wind turbine controller consists of a torque and a pitch control. So here we see our control view. The load effective wind speed is disturbing the wind turbine. The important measurement signal with the generator speed, and with the torque controller, we then adjust the generator torque to low rated wind to optimize the power production, and above rated wind, basically most often we try to maintain rated power. Then we also have a pitch controller, which compares the generator speed to the rated generator speed, and then adjust the pitch angle. And this is done above rated wind, below rated wind, which is mainly inactive. And then we have also some interaction for the transition between pitch and torque control. So that's the basic control loop. We now focus on the pitch control. So the pitch controller, as I mentioned, is mostly active in region 3, where we already reach maximum power and rotor speed. And the pitch controller aims to get power and rated speed constant. And since in this equation of the electrical power, if the wind speed is going up, we need to reduce the pitch curve. So the pitch angle will go down to zero. And this results in the static pitch angle here over wind speed to reduce the power curve. And at the end, there's a compromise between speed regulation, reduction of structural load, and pitch activity. So, for Lidar-Assisted control, or for default control, we want to assist the pitch controller in full load operation. So in this case, the pitch controller is maintaining the rated speed, and the torque controller the rated power. How can we do that with default control? How can we keep the rotor speed constant, which means the acceleration is 0, if the wind is changing? And in this case, we can use the static pitch curve, cancel out all effects of changes in the wind to the aerodynamic torque. Right? So if the wind is changing and we adjust the pitch angle according to this static pitch curve, the aerodynamic torque will stay constant, and then the rotor speed will be constant, and also the generator torque as well. So that's a very simple concept. And the advantages are here. It's a simple update to conventional feedback control, right? So you have a feedback controller and then you can assist the people. And that's very important because you go to a turbine OEM and tell them, okay, I want to replace your control system with something new. They most likely will not be very happy about it. Because they also invested a lot of time in feedback control, and they know their turbine best. But assisting them doesn't come. Then it also works over the entire full load region, right? So it's really nonlinear control of we use this depending on the million speed. You need very little model information. That's the only thing you need. Static system. And for control engineers, also very important, you have guaranteed stability. So you cannot make the closed loop unstable. Since the closed loop, like a feedback loop for the feedback controller, which is stable, the process is stable because it's a simple curve, you cannot make it unstable because both are independent. Okay, so how does this work? Here an example where we simulate the 5 megawatt turbine with fast, the aeroelastic code, and we have a coherent wind extreme operating gas at 25 meters per second. So this is this extreme operating gas, because of magnetic head, and that's typically used to test control. And here with the feedback only, we need to wait until the gas cause changes in the rotor speed, and then the pit can react. And you can see the pit react a little bit late. Here we reach already maximum generator torque, and this is generator torque twice to maintain the power constant. And the crossover will move quite a lot. And this is very harmful for the power. Now with the support control, we can follow with the pitch our wind here, and then get the rotor speed almost constant. So that's the full model one. So that with all the freedom, and still we get very fast rotor speed, which means it's quite robust to model uncertainty. And a nice side effect is that also the power will move much less. This is because for high wind speed, torque and thrust look like similar. Okay, so just one example with perfect wind preview. So when you know the wind perfectly. How will this change when we have realistic preview? So here simulation study, again with the fast model, but now with turbulent wind and a lighter simulator. We use wind extraction and the adaptive filter I mentioned before. And here you see power spectral density, rotor speed, and power base bandwidth. And since we use this adaptive filter, we have no negative effect for uncorrelated frequencies. So here, blue and black line are the same. But for the low frequencies, we can get reductions in the rotor speed spectrum and also in the power base bandwidth. We can also display it over lifetime for different mean wind speeds. And then we see here that the damage equivalent load for the power base bending moment can be decreased for high wind speed significantly. The overall lifetime reduction, the overall del reduction is about 10 to 20%. And already 10% means that we can operate the wind turbine 50% longer. And you also get benefits for blade stuff, and also a little bit of energy increase because you avoid sitting below it. And this simulation shows that the whole concept is robust with respect to the measurement from terms. And this has been conducted already a long time ago. And when the National Renewable Energy has seen this simulation, they invited me to do some field testing on their research turbines. So those were hard turbines, like the control advanced research turbines and NREL, They are pretty small, like 600 kilowatts, but still, as I here you see the container compared to human beings, still one. And we have two LiDAR systems itself, or scanning LiDAR on the two-bladed one, and a LiDAR, a commercial LiDAR with 3 points on the three-bladed one. And it was like independent cooperation between SW and NREL, and the focus was on speed regulation. And the good news is, and we were really happy that after the field testing, we were able to show that we definitely can reduce the rotor speed spectrum. Here, like the standard deviation was 30% reduced, which is like the area below the curve. And this was to say the result at the end. Again, blue is combined feedback before. However, in the beginning, it looked like that, like the red clip. So in the beginning, we got even more load for certain frequencies. So what happened in this? So there was a magma in front of the turbine, and therefore the LiDAR was sometimes measuring 0 meters per second. And this disturbed our signal, and we got negative. So what do we learn here? Checking the correlation is very important before you apply it. Best would be to constantly check it and to be more adaptive if the quality goes down. So in general, what are the benefits LiDAR system control? So in the first field testing, we showed we can get into speed regulation. Then during my postdoc, I went to NREL again. We could show that we get more load reduction when we retune our feedback control. When we are a little bit more aggressive with the feedback, we get even better with more load reduction, and also we tested their more adaptive filtering. However, load reduction cannot be directly used to get more money, and therefore more energy is better. There are several possibilities to get more energy, and the most common one is either upgrade your turbine. We can run it on a higher power level if possible, and then you can get more energy every year. Or we can do a lifetime extension, right? So you can just run it longer and therefore get more energy over the life. So what is the status of LiDAR system control? So currently, I think there are already more than 3,000 turbines running with LiDAR system control, mostly operated by Goldman. So we had like a press release here already some years ago, and at this time it was like 6 gigawatts running with LiDAR system control, and it was like our first project how we founded our company was when we supported Goldwind to use this technology. We had like further industrial collaborations between Meta, Miss Laser, I need to add here later as well. And well, there's still challenges, right? So Goldwind is until now the only OEM who uses this certified LiDAR system. But from what I know, that also Ignition is already working on it. And maybe they even finished the certification. And like Goldwind and Ignition are top 1 and top 2 of the OEM worldwide. So there's still some challenges. One challenge is the complexity of the economic benefit, because everyone agrees that we can reduce the. But is this really making an impact on the economic? That's depending a lot on your turbine design, a lot of others. And you need to be robust. You really need that will really have impact and certification. You need to show that it works under all conditions, or also if the LiDAR is not able to measure, that you still don't get negative. And therefore, it's really important to be invested. So to approach these challenges, we think that the smart LiDAR concept might be very helpful, because it always takes a lot of time to develop new algorithms, to test them on the turbines, because of the safety criteria of the turbine. So if you want to change something in the turbine controller, you need to do an extensive simulation study. You need to do then also hardware intelligence testing, and before you can do a field test. And therefore, we propose to use the LiDAR system more like a smartphone, right? So that you can have, for example, here on a LiDAR system, the LiDAR data processing from the OEM. But the idea is that we can also use like open source LiDAR data processing from researchers, or also third-party algorithms from companies like Sowento, which we can load onto the LiDAR, but also can use in simulations for certification. And this would accelerate the whole development. And we had a PhD project in Flensburg working a bit on this idea. It was part of the LIFE Marie Curie network. We also include Denmark and a lot of other universities involved with how we met each other first time, right? And then now we're working at postdoc in High University. And together with Feng, we also published the IA Wind Park open source tools, where we made a tutorial on loading wind turbines. And I should add the paper. It was like published in the American Control Conference 2 years ago, and here you can also see that for floating wind turbines, for example, with motion compensation, I mentioned earlier, it's very important. But if you don't use this motion compensation, which is the red line, you could even make your floating turbine to become unstable. If you have the motion compensation, you can really use also the video of the LiDAR to improve the control of floating wind. And this concept we also use, or the code we also use in the LiDAR system control summer games. Was in the national competition last year. We also in the university participated, and we now having a second version, which is Summer Games 2025. The motivation is to share knowledge, and we also want to share our enthusiasm with students, because LiDAR-Assisted Control is really helpful. So all wind turbines should be able to see. We don't want blind wind turbines, right? So, and we have here 3 different disciplines. The one is the 30-second sprint, where we simulate the 30-second gap. Which is good for control and students. And we also have this 18 meters per second hurdle, which is, I think, very good for data scientists. And then we have also a challenge which is called the DLC, like the time of phase 1.2 marathon, where we simulate the whole lifetime of the program. And how can you participate? So you can try the code on GitHub. So in the simulation I can share later, there will be a GitHub link. You can also check the results we just presented in like 2 months ago in Hainan. Yeah, please mobilize your students and colleagues to participate in this. And the lecture of this week at the end, participation here will be part of the course. So, I would like to use the remaining time to quickly present some results from our current research project. So this research project is called Adaptive Operations for Existing Wind Turbines